extraordinarily pleased to welcome today Professor Ángel Serrano from the University of Valencia in Spain, the Catholic University of Valencia in Spain. You folks will remember that earlier in this series this year, we had Bob Langer speak to us. And, I was impressed with Bob's comment that he wanted to make sure to use his science and engineering to help people. And that's an attitude that Ángel shares with us today. Science, in my view, science and technology are at their best when they really do serve a useful and meaningful purpose for people. And we're going to hear that from Ángel today. Ángel, I'm going to welcome you to the forum, but I want to turn to Ron Smith for just a moment to add to my introduction, since you and I and Ron have had many conversations over the past few years. So Ron Smith, you're muted, but if you would say a few words, that would be great.
Just unmuted. How's that? Can you hear me now?
Yes.
Sounds like a bad ad. Well, welcome to my friend as well at the same point. We first met. One of the things that Innovation Toronto does every now and then, and not often, is reach out to people who are doing very important work at very important times. And our friend here today is one of those people. We met online. I had approached him basically saying, was there anything that we might be able to do to help with the MASS project? Because we were right at the beginning of COVID and it looked like things were getting bad. We did not have a lot of resources in Canada, in the United States, and a lot of other places to be able to meet the challenges that the disease was throwing at us. So he very kindly started a conversation. We started going back and forth to see what, if anything, we could do together. Got you involved at the same point in terms of being able to try and help out. And here we are today, somewhat 4 years later at the same point. So it feels like an old friends meeting.
Yeah,
and I am very, very pleased to listen to the update and see what's going on in that world.
Thanks, Ron. Well, Ángel, I think we're ready now. If you would like to share your screen, and we'll go forward with your presentation. Welcome to the Wilson Forum.
First of all, thank you very much, Ron, both Ron, for your invitation to this forum. And well, I am Ángel Serrano from the Catholic University of Valencia. I work as a professor of biotechnology, and I am also the principal investigator of the biomaterials and bioengineering lab. I have divided this presentation in 6 sections. I will start giving an introduction to for those who are not familiar with biomaterials field. Also, I will introduce a very important problem that we have nowadays in health that we are very concerned about it, that is bacterial resistance. And then I will go to the developments that we have produced in my lab about the development of antimicrobial face masks with several technologies, and antimicrobial face shield and antimicrobial lipstick. And finally, I will talk about ongoing and future studies that we are carrying out. Well, for those who are not familiar with the biomaterial fields, biomaterial is, according to the first definition, is a non-viable material used in medical devices trying to interact with biological systems. So the biomaterial science is, we could say, that is the study of materials with a special reference to their interaction with the biological environment. And one of the most important that a biomaterial have to fulfill is to be biocompatible. And biocompatible, it means that they have to have ability to be in contact with a living being without producing any adverse effect. The field of biomaterials is relatively young. We are talking about 60, 70-year-old, but nowadays there is a huge industry. I'm sure that many people from your family have used biomaterials in their bodies. There is a lot of biomaterials used today in cardiovascular, orthopedic, dental, ophthalmologic, reconstructive, biodegradable surgery, and biodegradable sutures, bioadhesives, drug release. Thanks to biomaterials, millions of lives have been saved, and the quality of life of other million people have been improved. In my group, we work in this field in the development of new biomaterials for biomedical applications, and we are also very concerned about the real problem that we have nowadays, that is bacterial resistance, because the resistance to antibiotics is nowadays one of the greatest threats to global health. They are saying that it could be the next pandemic. And according to the World Health Organization, it is estimated that the number of deaths from this cause will surpass those produced by any other disease, including cancer, by the year 2050. So bacteria has the ability to develop resistance to antibiotics, and it becomes a moment and the antibiotics are not effective, and the bacteria can kill yourself. Therefore, there is an imminent need to find new antibacterial materials capable of preventing and treating multidrug-resistant infections. So in my group, we are working on biomaterials, and also especially when it started the pandemic, we were working with alternative materials to antibiotics that they could kill these multidrug-resistant bacteria. And we started, from the beginning of the pandemic, we started working in the development of antimicrobial face masks, because face masks are made of materials that are biomaterials, because they are materials that have to be in a biological environment, that is the skin, without producing any adverse effect. They have to be biocompatible with your skin. So there are many studies that they have proved that face masks are very effective tools to prevent viral and bacterial infections. We have learned a lot that there are a lot of face mask types. Depending on the application, you can find surgical masks, N95 masks, FFP3, depending on the application. Face mask can protect yourself when you wear the face mask, because it acts as a physical barrier. That is a porous filter that what it does is to avoid that virus can get through your airways and you can infect you. And also it protects the other people, because when someone is infected and you wear the face mask, you are not infecting other people, or the viral particles are much less than if you don't wear the face mask. We have learned in the pandemic that, especially with the SARS-CoV-2, that is the virus that produced the COVID-19 disease, that it was like a new way of transmission, that it was through aerosols, especially in indoor places. And we have learned that when people are laughing or coughing or breathing, they are releasing these aerosols that contain viral particles that can infect people, and they can reach even 6 meters, a distance of 6 meters. However, conventional face masks are made of materials that are not antimicrobial. They are made of materials that what they do is to block the path of the virus, but the virus remains active in the face mask. The virus or bacteria remains in the face mask, and then if you touch the face masks and you touch your eyes, or you touch someone, the transmission of the disease can be produced. Therefore, in this project, what we thought is that we could develop a face mask that it was made of antimicrobial materials that when the virus or bacteria is in contact with this material, they are destroyed. And we try to achieve a method that they could be destroyed as soon as possible to be more protected. So we are starting this developing one technology that it was antimicrobial face mask produced with a bioactive coating of benzalkonium chloride. Benzalkonium chloride is an organic salt that classified as a quaternary ammonium compound that has been approved by the FDA as a preservative in liquid formulation for topical, ophthalmological, and nasal. And we knew before the pandemic that this compound was effective against a wide range of bacteria, yeast, and fungi. And from before the pandemic, in my group, we were already working with this compound as an alternative to antibiotics to try to kill multidrug-resistant bacteria. The antimicrobial mechanism of action involves the perturbation and disruption of the membrane bilayers of the microorganisms because of the electric charge that it has on top of the nitrogen atom. So what we did was, by the famous industrial method of fabricating, that is the deep coating method, what we did was to produce a coating, a micrometer coating, because we had to produce this coating, but we had to achieve that afterwards the face could be used and you could breathe and you could. So what we tried is to make a very, very tiny, very thin coating that it would not modify the morphological properties of the conventional face mask. Well, we achieved this by the deep coating method, and we could see by electron microscopy that the morphology with the controls and the filters treated with BAC, the benzalkonium chloride, was very similar. So what we did is we wanted to try this antimicrobial face mask against SARS-CoV-2 during the beginning of the pandemic, and we tried to contact a lot of labs in Spain, Norway, and other countries to try them, but at the beginning of the pandemic, all these labs that they are biosafety level 3 labs, they were very busy trying drugs, developing vaccines. So it was impossible for us to try this at the beginning, to try these filters against SARS-CoV-2. So what we did is we decided to find an alternative virus that it was very similar. That is the bacteriophage physalis, as you can see here. This virus is a virus that infects bacteria instead of cells or humans like SARS-CoV-2. So you can use this virus in biosafety level 1 conditions. So you can use in any lab. It's very easy to work with this virus. So we started working with this virus, and we placed the virus in contact with the face mask, and we could see that after being in contact, then we would place the virus in contact with the bacteria to see if it was able to infect them. And we could see that after we started with 30 minutes of contact, and we saw that after 30 minutes, the virus was inactivated and was not able to infect the cells. As you can see in the controls, that you can see white spots here, that it means that the virus has been infected. When you place the virus with a conventional face mask for 30 minutes, it does not inactivate the virus. However, with these filters, it does. And we started reducing the time of contact, and we achieved also that in just 1 minute of contact, 100% of the virus was inactivated. So when I got these results, I contact a professor from the university in Kyoto that I was lucky that I met in a meeting, and he told me that he was working with SARS-CoV-2 there in Japan. And I told him and I showed him all my results. And so he told me to send him the filters of the face mask, and he tried them against SARS-CoV-2, and he also saw that more than 99% of the virus was destroyed after just 1 minute of contact. So this was a very good result that we had at the beginning of the pandemic. And But we wanted to know also, since benzalkonium chloride is a potent antiseptic, we wanted to see if also these face masks were able to kill multidrug-resistant bacteria. And we tried these filters against methicillin-resistant Staphylococcus aureus and methicillin-resistant Staphylococcus epidermidis, that are very important pathogens. And we saw that also it was able to kill these bacteria, as you can see here, a circle, that it means that all the bacteria around the filter was dead. With this study, we also demonstrated that we could use this virus, the bacteriophage that infects bacteria, as a biosafety model of SARS-CoV-2. And this could be very useful for many labs that they don't have biosafety level 3 labs to start working and developing new compounds that could be useful to treat or prevent SARS-CoV-2 infection. We published these results of this study of this antimicrobial face mask as a preprint first, and then in an open access journal, so that everybody in that moment could use these results to improve their companies that were producing face masks, because they could use in all the world, they could use these results to improve their face masks and make them more effective, and try this, and in this way try to help as much as possible. In that moment, that in Spain were dying a lot of people, and also in Italy at the beginning. That's why we decided not to patent this development and publish it in open access. So after this publication, we got a lot of famous in Spain, because a lot of the television and all the newspapers everywhere, they were announcing that we had developed a face mask that can kill SARS-CoV-2, and we have tried for the real SARS-CoV-2. And then a lot of companies try to improve and incorporate this technology in their face masks. And we got an agreement with Med, this company from Alicante, that and in only 3 months we tried to work very hard to make this happen as soon as possible. And in 3 months, they were selling massively this kind of face mask, and with the goal that we have in common to produce this face mask at a very low price. We could do this. That is the conclusion of this project, is that we develop a low-cost technology, because benzalkonium chloride is a compound that is industrially produced and it's very cheap. So this was a very good point about this technology. And it can inactivate SARS-CoV-2 in seconds. This is also very important, because during the pandemic, a lot of researchers have developed face masks, but to be effective in only less than 1 minute, I have not seen many, because most of them inactivate the virus after 2 hours, or 3 hours, 5 hours. But we believe that if you want to have a real protection, you need to inactivate the virus or bacteria as soon as possible. So the good thing also about this technology is that you can get protection with this face mask against multidrug-resistant bacteria. So that means that it could be useful also after the pandemic, because multidrug-resistant bacteria is a very real threat for humans nowadays, and they could be very useful for people, for example, that are working in a hospital, and they can be more protective from this kind of bacteria. Since we use the bacteriophage fish, which is an envelope virus, like influenza, we believe that it probably protects you also against influenza. We get a protection in 2 directions, as I mentioned, because people that are infected, you can, with this face mask, you release the virus, and most of the virus that you release get inactivated. And also when you wear this face mask and there are people around that are infected, but you get protection also. Besides, we achieved a reduction of infection biological waste, because we know that during the pandemic, a lot of people got infected. People working with waste management got infected because there were so many face masks with the virus and that. So with this technology, we also reduce this type of waste, and we got the production at industrial level. Another technology that we developed afterwards, with the goal also is to produce a low-cost technology that it could be used in all the world, and even in undeveloped countries with very low resources. And it was making use of the knowledge that we knew about hand soup. Hand soup, we, at least in Spain, always on TV, they were saying that we have to wash our hands often, because that was a good way to prevent the COVID infection. So, and according to the World Health Organization, hand washing, they have announced that it's an effective tool to prevent COVID-19. We know that the antiviral action of hand soup is mainly attributed to the surfactant molecules present in the hand soup, and the mechanism of action are attributed to membrane rupture, simple elution mechanism, or viral entrapment. There are several proposed mechanisms that can destroy the virus. So with this idea, what we did was to produce a face mask that it could have a solidified hand soup coating that could kill, could act as an antiviral agent. And what we did was that a conventional face mask with we will produce by deep coating also a coating of hand soup that we will dry to get it very solid, and then by electron microscopy we could see that the morphology was similar, it didn't change. We also tested the breathability to check that it was the same before and after the treatment. And we tested also this virus against bacteriophage, that is the virus that you can work in biosafety level 1 conditions. And we could see that also after 1 minute of contact with the virus, with the contact of this face mask, got inactivated or destroyed, and they could not infect the cells of bacteria. We send the samples also to Japan to test them against SARS-CoV-2, and we also saw that more than 99% of the virus got inactivated, SARS-CoV-2, after just 1 minute of contact. We check also that these face masks were non-toxic, because that was another concern that we had. If you have their solidified hand soup, maybe if you breathe this hand soup, it could be toxic. And we perform a test, a cytotoxicity test, that is used for medical devices, and we saw that it was that 100% of the cells continue alive after the test, according to, and we follow a norm that is ISO norm that is commonly used for this test. That this test is usually employed for prostheses, scaffolds, things that are inside the body. This low-cost technology can also be applied to other infection prevention clothing. We propose that we can use also the similar procedure to produce antiviral caps, scrubs, shirts, trousers, disposable gowns, overalls, shoe covers, many of these clothing that is used especially in hospitals and can protect people working there. So the conclusion of this project was that we have developed a low-cost technology also that inactivates SARS-CoV-2 in seconds. It is an infection protection tool to combat COVID-19 and future pandemics in developed and underdeveloped countries, because taking this paper, maybe anyone could produce antiviral face masks at home. protection against other enveloped viruses, such as influenza, protection in two directions, like the other development. And also with this, we could achieve a reduction of infection biological waste. And the third technology that we developed during the pandemic was antimicrobial face masks, but produced with biocoatings of cranberry extracts, which is a bio-based technology. The goal of here was to use a coating that it was biodegradable, renewable, and more natural. So for this project, we used cranberry extracts that we knew before the project that they are already used as in medical use for treatment of urine infections with bacteria, and they have shown antiviral activity against enveloped viruses like herpes, simple virus type 1 and type 2, and influenza. So we thought that since they were active against this type of viruses, that they are enveloped viruses, they could also work against SARS-CoV-2 and also against multidrug-resistant bacteria. And we know that the cranberry extracts contain A-type proanthocyanidins that are compounds that affect the viral capsid of the virus and alter its glycoproteins, leading to complete viral inactivation. So the goal was to use cranberry extracts and see how we could place these cranberry extracts as a coating on the face mask. And we developed this technology also using the deep coating method, fixing the right concentrations and method and solvents. And we could see by optical microscopy, the microscopic morphology, that we could see a reddish color, but a similar aspect. And in by electron microscopy, we could see that the morphology was also very similar, that it did not affect the morphology. And then we tried the face mask against first of all, we always work before with the bacteriophage physae with this virus, that you can work in biosafety level conditions, and you can do as many things as you want. And then when we know the right time and the right condition, then we send the samples to Japan, because it's very hard to work in a biosafety level 3 lab. So we tried directly the filters against this virus with 1 minute of contact, and we saw that more than 99% of the virus was also inactivated. We sent the sample again to Japan, and we saw also that an important reduction of viruses, more than 99%, was achieved using when they were placed in contact with this face mask. We tested the face mask, that you can see that they have a reddish color. We test them against multidrug-resistant bacteria, and we also saw that the bacteria died around the filters. In order to know that this technology was safe, in this case, we use a test that what we do is we produce a extract of the face mask, and then we place this extract in contact with the worms, that is the C. elegans model, that is very commonly used in biotechnology, because it's a worm that shares a lot of genes with humans, and it can be very useful as an in vivo toxicity model. So what we did was to study its survival rate, growth, see how they grow, if it affects the extract to the growth and the reproduction. We saw that the survival rate, one moment, sorry. But it did not affect the survival rate, because according to the standard norm, more than 70% of the worms were alive after being in contact with the extracts of the face mask. The growth also was not affected, and the reproduction was not affected. Therefore, we could conclude that these face masks were not toxic. This technology can also be applied to other infection prevention clothing. You know that they would get the red color, but it could also be as a natural treatment to produce all this equipment with cranberry extracts. So the conclusions of this project was that we have developed a bio-based technology that inactivates SARS-CoV-2 also in seconds. We use here renewable and biodegradable materials, cranberry extracts. We get protection also against multidrug-resistant bacteria, so they can be used in hospitals or anywhere to protect you against this threatening bacteria. Protection against influenza also, protection into duration, and we achieve also a reduction of infectious biological waste with these treatments. We have also developed, in collaboration with the University of Wolverhampton in the UK, filters that antiviral filters that they are produced by 3D printing, and they are metallic. So they can be used in systems from purification of air, and they can also, because they are antiviral, when the virus gets in contact with these filters, gets inactivated, destroyed. And another development that we have achieved in my lab is the development of antimicrobial face shields. We know that face shields are also effective tools to prevent viral and bacterial infections. You know that in hospitals, they are commonly used, especially when there is a surgery, and sometimes they are used also with face mask and face shield altogether. But face shields, the conventional face shields are not made of antimicrobial materials. So that means that when a virus or bacteria get in contact with the face shield, they remain there active. So if you touch the face shield afterwards, or you touch your eyes, or touch your mouth, or touch someone, or you can infect people. So with this goal, what we did was to try to develop a face shield that it was made of a material that when the virus or bacteria touches the surface of the material, it gets destroyed as fast as possible. For this achievement, what we did was to create a coating produced by also benzalkonium chloride. Why we choose this compound? Because it is transparent. And in this project, it was very important to keep the transparency of the face shields. Otherwise, it was not possible to use them. So what we did was to create a very thin layer of benzalkonium chloride around the surface of the face shields that we could see by electron microscopy, that it was very transparent, so it does not affect the transparency, and we measure the transparency to check for sure that it was not affected, and we could see that it was the same. We also tested these face shields against bacteriophage feces, and we could see also that after 1 minute of contact, 100% of the virus was destroyed. We sent these samples also to Japan, to Kyoto University, and we saw that also more than 99% of the virus was inactivated after 1 minute of contact. We test them also against multidrug-resistant bacteria, and we also saw that these face shields could destroy bacteria very fast. And this type of technology can also be used for other equipment, like, for example, for helmets, goggles, separation screens, and they have the property of, as I told you, that when the virus is in contact with the surface, it gets inactivated, and also bacteria, multidrug-resistant bacteria. So the conclusion with this is that also we have developed a very low-cost technology, because as I told you, benzalkonium chloride is very cheap, that inactivates SARS-CoV-2 in seconds, protection against multidrug-resistant bacteria, protection against other enveloped viruses like influenza, bioactive coating that keeps the transparency of the face shield, and we achieve a reduction of infectious biological waste also with this technology. And finally, the last development in my group was the antimicrobial lipstick. We know that lipstick are usually associated with higher physical, sexual, and social attractiveness. And we know that they are not usually made of antimicrobial materials. But we also know that many infectious viruses transmitted through the lips, like, for example, herpes and Epstein-Barr, the kissing that produces the kissing disease, is produced through the lips. So in this project, what we tried to do was to develop a lipstick that it had antimicrobial properties. And if this was achieved with a natural compound, it was better. No? And since we had seen that cranberry extract were so powerful killing bacteria and viruses, so we decided to incorporate this cranberry extract in a common composition of a lipstick. Mm-hmm. We tested this lipstick against two types of viruses that are also used in biosafety level 1 conditions, that is bacteriophage physace and MS2. We use these two viruses because one of them is an envelope virus that can be used as model of many other envelope viruses like SARS-CoV-2, influenza, and many others, and MS2, that is a non-envelope virus that can be used as a model also of hepatitis A or other disease. And also we know that, well, and so what we did was to test them against this type of viruses to have a broad spectrum antiviral study. And we saw that with bacteriophage physace, after just 1 minute of contact, even creams used for the lipsticks in very low concentration would destroy 100% of the viruses. And with the other virus, MS2, the non-enveloped viruses, the creams with higher concentration, 6 and 10%, would kill also more than 90% of the viruses after 1 minute of contact. We know that non-enveloped viruses are stronger, more difficult to destroy, and that's why we got these results. But we saw that also this kind of viruses can be destroyed with this antimicrobial lipstick. We test these virus lipsticks also against 4 other microorganisms, against multidrug-resistant bacteria like methicillin-resistant Staphylococcus aureus, and we saw that after 5 hours with low concentration of cream, the bacteria was killed. And we tried also this against a gram-negative bacteria, that is Escherichia coli, and we saw that after 2 hours also they would die in contact with the cream used for the lipstick. And also we test them against a Mycobacterium smegmatis that is commonly used as a model of Mycobacteria tuberculosis. That is very important health problem nowadays. And we saw that also it was effective against this type of bacteria after 5 hours. We test them also against a yeast, a pathogen that is commonly used, that is Candida albicans. And we saw that after 15 hours, it was also destroyed, this pathogen. So the conclusion of this project is that we have developed an infection prevention tool made with natural red colorants that are renewable materials. With these lipsticks are red because of the cranberry color. They have broad spectrum antiviral properties against envelope viruses such as SARS-CoV-2, herpes, influenza, and Epstein-Barr, and non-envelope viruses such as hepatitis A in less than 1 minute of contact. Broad spectrum antimicrobial properties also against multidrug-resistant bacteria, MRSA, E. coli, and a surrogate of the tuberculosis and Candida albicans. So finally, the ongoing and future studies that what we are working nowadays, we are also working in the development of next generation face masks. Our goal now is to produce face masks that are biodegradable, antimicrobial, and also biodegradable to face the huge problem that we have with the massive use of face masks, especially during the pandemic, that is producing to our environment. So our goal is to develop a biodegradable face mask that is antimicrobial. It can kill viruses, bacteria, and is biodegradable and at a low cost, so to be possible for a commercial company to produce it. So it's very challenging, but we are working on that. We are also working in the development of the antimicrobial face shield with biodegradable properties. Face shield that could be also biodegradable and that way could be better for our environment. We are also working on the application of carbon nanomaterials as antiviral agents in collaboration with the University of Pennsylvania. We are working because these materials are next generation materials that the most famous is graphene, but we have observed that they have potent antimicrobial properties against bacteria, virus, and fungi. And so, and they present an important fact that is that the antimicrobial mechanism of action is more physical than chemical. Therefore, we believe that for microorganisms will not be able to develop resistance to this kind of material. So nowadays it is in the infancy of this knowledge, but we are working and trying to, because they present also some problems about toxicity, but we are trying to manage all these problems and overcome these problems and see how if it's possible in the future to use these materials. They can also be used in combination with other materials to produce antimicrobial, for example, ceramics, or for walls in hospitals, or in combination with metals and elevators. Some antimicrobial material that can reduce infection, microbial infection transmission. We are also working in the development of an artificial bladder in collaboration with the hospital of the University of Valencia and also the research center that we have here. In this bladder, what we trying to do is we're trying to use bladders from pigs that can be decellularized. You can remove all the cells from them and then seed them with cells, stem cells from a patient. And then when you implant them, there is not a rejection. And we are working with this in the field of bioreactors. We are also working in the development of scaffolds by 3D printing for bone regeneration, materials that can be biodegradable. I can be implanted in someone that has lost a big piece of bone because of a disease or an accident, and they can be implanted and regenerate the bone. So we have already get good results with rabbits, with some scaffolds that we have developed, and these scaffolds have osteoinductive properties and also antimicrobial properties to prevent infection. We are also working in the development of new antiviral compounds produced by microbial culture. We have seen that there are many microorganisms that release antiviral compounds. that could be very helpful for to try to destroy viruses, and we are working in this. And finally, we are also working in the development of probiotic drinks, probiotic beer and probiotic wine, in collaboration with some wineries and brewery companies in Spain. We have already developed a probiotic wine and a probiotic beer. That probiotic means that it contains, at the end of the process, it contains alive microorganisms that are very good for your microbiota. These microorganisms are, what we have used is Saccharomyces cerevisiae barbolardi, that is already used nowadays for many treatments when someone has a problem of diarrhea or some intestinal problems. They are already used. And what we did in this project was to fermentate the mast with these microorganisms, and the goal was to achieve a large amount of alcohol without killing the microorganisms. And at the end, because at the end they have to remain alive, these microorganisms, so that it is has the probiotic properties. We have checked that the microorganism remains alive in wine after even 6 months, and so they come in fridge conditions and also at room temperature. So it can be very interesting also for the winery company. And this is all. Thank you so much for your attention. This is a picture of my group. We are not many people. We are young. Well, me not so much, but
Well, thank you. Angel, you know, I said at the beginning of the morning when we met that science and technology are literally at their best when they serve the best interest of people. And you've given us a magnificent demonstration of that this morning. And I just want to say you have my loud applause for the work you're doing at the university.
thank you.
You know, the work is global in character. You have research partners in Norway and Japan, in the US, as well as in Europe, which is remarkable. And this technology is shared, which I find even more remarkable. So I have a couple of questions before I turn over to the other folks in our group. You know, there will be other. We're not beyond. Let me back up. We're not beyond COVID at the moment. That's clear. But there will be other pandemics and epidemics in the future, and we need to be prepared to deal with them. So what you've done, for example, must be enormously appealing to hospital staff, medical staff, to think that you can produce not only masks, but antimicrobial clothing and fabrics to protect the staff. Remember all of the incidents of hospitalization of medical staff during the early stages of COVID. The hospitals couldn't meet the patient demand, but they also couldn't keep their staff healthy. And what you've done is provide a means of doing that, which I find absolutely just enormously important. So my two questions are, number one, you said that this technology is not patented. Is that correct?
Yeah, it's correct. None of this technology is patented.
And why is that?
Well, we decided not to patent it. When we started the first technology, it was the critical moment that there were dying a lot of people in Spain, Italy at the beginning. So we didn't want to lose time patenting. And what we did was to try to help. And I thought that the best way to help is to publish, to make it free for any company. That was my opinion, and other people also thought that it was, also at my university, they thought that it was better like this. That's why we patented, we publish it in a preprint that anybody could use it. And I think that for that reason, also some companies got interested, because if you patent it, you can lose time, I think. And it was a time, very stressful time, that we wanted to produce the face mask as soon as possible
Yeah.
to help.
You know, to be really honest, I did know the answer to that question, but I wanted the rest of our group to hear that. What you've done is truly, truly monumental. Because you wanted to get it to the people fast, you chose not to patent it. You could have patented, and obviously the consequences would have made you, I imagine, pretty wealthy. And there have only been a few occasions where that has not occurred. Jonas Salk never patented his polio vaccine for the same reason. So I give you my heartfelt applause for doing that. I see Ron Smith's hand, so let me turn to Ron.
Well, let me put it this way. When we first got involved with the idea of trying to find a mask that would help
Right.
at Innovation Toronto, we went global, looked at a lot of people doing a lot of very good work. And what stood out about what Professor Serrano's work was doing was his willingness to do precisely what you've highlighted, Ron. That's what caught our attention to begin with.
Right.
Also, the fact that he was looking very much at the distribution side of it to make sure that there was equal distribution between companies that were wealthy and have countries and have not countries at the same time. So the purpose for us, at least being non-scientists, but the purpose of science is to serve. And I think we have a grand example of someone who's doing precisely that. Fabulous work and applause as well.
Right. Thank you. Let's take some hands. We have two hands. I see Eddie and Martin. Let's go to Eddie first.
Yes, well, first of all, I definitely add my commendation to everyone else's. I think it's fantastic. And personally, I've been getting less and less happy with the whole patenting system, which sometimes I think works against, I would say, the general good. It may work for certain organizations, but I think it's gone excessive to today. So definite commendation. But I have several questions, but I'm going to be specific about two of them. One is that in dealing with potential pandemics and so forth in the future, even though we may apply it to just hospital clothing, what about general clothing? Would it add that much to, for example, to dyes and other common technologies that are used in the production of normal clothing that could help us possibly prevent pandemics from really spreading out? Maybe even in sprays, for example, in clothes and that kind of thing. So that's one question I have, and whether anyone's ever done anything. The second question I have is rather more space related. In space, you have a big problem with potential contamination. One in particular is with things like lettuce, which is grown in space, which turns out to be very prone to salmonella disease. And is it possible that one could develop sprays and that kind of thing? This is actually one of the potential problems with going into deep space missions. So I'm wondering if that any work has been done in that area. And I'd also like to say hi to Caroline, because I hope we'll meet very soon.
Thanks, Eddie. Angel, do you have a comment?
Well, I agree with you that it could nowadays it could be possible to produce antiviral clothing for everybody, and it could be a way of avoiding transmission, of infections, and also it would be wonderful if, for example, especially in airports, all the ceilings and walls would be made of antimicrobial materials, because in these places that there are so many people coming from so many countries and so many transmission that there is there. and also in airplanes, buses, everywhere. I think that would reduce a lot the transmission of diseases. So I agree with that opinion. And
Just a
yes, sir.
corollary question. Are the fabrics now commercially available at hospitals, for example? I mean,
No,
they are.
as far as I know, no,
Not yet. Oh,
not yet.
and is there a vehicle for making them available commercially to hospitals? Do you have a plan to do that, or does the university have a plan to do that?
We try to do it with the Visormed company.
Yeah.
We start doing with caps and but I don't know why they were not interested in that. They were only interested in face masks. Sometimes, the little increase of price and the production, and sometimes doesn't things doesn't get better because of that, or even people don't really appreciate what they are wearing, because sometimes I remember that when we started producing the face mask, antimicrobial face mask, people would tell me, but the other face masks, they don't kill the virus, they don't do anything. It's because it's difficult to explain everything for the general public.
Well, let's turn to our attorney, Martin O'Donnell. I'm just curious about your thoughts on all of this associated with patenting. I should say I'm not opposed to people patenting things and becoming wealthy. I think, frankly, if in fact the patents serve a social purpose, then everybody needs it. I think that's entirely appropriate and suitable. I am impressed by Angel's wish to get this out to the public quick, and therefore he chose not to patent. But I'm curious about your thoughts on the whole process. You have a lot of experience in this area.
Well, you have to distinguish between two things, the ability to do your work and get it out to the public quickly, and the ability to affect the work that others might do on that idea. A patent will not delay your ability to get the work out into the public at all, totally separate. You can keep on doing your research, your publication, your work in the public sphere while the patent process proceeds. So it doesn't slow you down at all. The purpose of the patent is to slow your potential competitors down. The second point is your work might not have been, somebody has to fund your work. And for many people, the possibility of profiting from their work is the impetus to seek funding and invest against the future. But you're not going to invest against the future if the moment you come out with something, someone else can take what you've already developed, use your knowledge and technology, and jump right in without having invested anything. So that's the purpose of the patent system, is ultimately to stimulate the idea of invention and dissemination to the public. If this idea is, if the participants in this research, et cetera, were not associated with universities which pay their salaries and lab fees, et cetera, it might not have happened unless there was a possibility of a payoff through something like patent. So yes, you slow down the broad public adoption by patenting it, but you don't slow down your own work. That said, it's a noble ideal. You've come up with something very, very useful, something very beneficial, and you want to make sure that the public benefits from it, and that's a noble ideal. And yes, I think in many, many cases, patents are overdone. I've seen some awfully junky patents that should never, ever, ever have issued. On the other hand, there's been some very good ones that have created whole new industries that might not have come into being, but for the possibility that your investment of time and money over a number of years won't be trashed by someone jumping on the idea once you brought it into the public without getting some compensation for you.
Yeah, I was just thinking that, in fact, I've often thought that there should be an alternative to the reward with regard to new inventions, and you know, a kind of a public recognition and ability to drive that forward into industries. And I think what Andrew has shown is that you can still do that, because industries still have the ability to do patents on how, for example, they could produce sprays and this kind of thing for the application of those inventions.
Very good.
I would like to
Ron
add
Smith?
some question. Could I add something? No, I would like to add, I'm not opposed against patenting. This was a special occasion, a special case, because we were in a dramatic moment, dying a lot of people in Spain. I was working mostly from home. We were all close at home, you know,
Yeah.
so that's why we decided to make this public, so that any company could use it very soon, you know.
Yeah.
Any company for free, they could use it. And I know that in England, China, I think also India, they are using this technology in some companies, you know.
Well, I have a suggestion. You know, I'm impressed by the fact that you've created lipstick. You could in fact make something for the public consumption that is like chapstick, you know, for not only for colorful lipstick, but chapped lips, and make that antimicrobial. I also like the idea of probiotic beer. I mean, come on, that's right in my wheelhouse. I like that. But I think, you know, I think the recommendations that I'm hearing would suggest that, you know, if you present work in public, I think, or publish it, I don't think you can then look to getting a patent. But I think, as I understand it, if it's not in the public domain, then the details, then you can patent it, and you can still issue it and you know, get it into the public, but you can still apply for a patent, I think. I'm not a patent attorney, but you've got a couple of good ones. In Ron Smith and Martin O'Donnell, you have two people who can really be very good advisors on these issues. But I like the conversation. I think what you're doing has enormous commercial potential, as well as the potential to serve millions and millions of people and help them with their health. Let's see. I see a whole bunch of hands, and I'm going to go in turn to Michael, Tom, Albert, and then Ron. But Michael, go ahead.
Okay, yeah, well, I'm unmuted. Okay, yes. Thank you for your presentation, sir. I agree with Ken, Martin O'Donnell. I have patents, and on one hand, I think it's really admirable to go open source and let everybody participate. But what I might do if I were you is I might patent one application like the lipstick, so that you can produce an income stream, because again, that lipstick I think is highly valuable commercially, while keeping the broad patent open source, so you don't interfere with getting the technology out publicly, but you still maintain a certain product in order to keep a cash flow to fund your own research. I would look at that. Also, it's interesting, I noticed that you talked about carbon, graphite, graphene. We produced biochar, and back in 2007, we went to Virginia Tech, where they ground 5 grams of our biochar, mixed it with a liter of water, and sprayed it on a surface contaminated with the 4 major aflatoxins of the time, and it bound to and deactivated significant percentages just by spraying a few grams per liter. And I'm interested in, I'll try to learn more about whether it's because of the graphene and graphite content of the biochar, or whether it was the biochar itself. But it did a pretty tremendous job. And Lastly, I'll just ask this. I notice you're using cranberry extract. Does that mean that if you eat cranberries, there is an antifungal and antimicrobial effect in the body?
We have not tested that. we have tested that when you place cranberry extract in contact with the virus or bacteria, they get destroyed. If you eat them or if you drink cranberry extract, I'm sure that all the viruses or bacteria that you have in your mouth and throat, because they would die for sure. If it can fix an infection that you have internally in your body, we don't know yet. I know that, well, they can, for urine infections, they are used in some mix with other medical drugs.
Yeah.
So it could be, but we will have to test it.
Thank
My
you very
affection for cranberries is growing by the moment, I have to say. It really is. Let's go to Tom. Tom, you're muted.
Yes, I have a question of how you found your way to benzalkonium chloride, seeing that many agents that are detrimental or kill viruses and bacteria are also toxic to us. Did you have a special protocol or a special path to finding that compound?
Well, this compound is like most compounds, that they are toxic depending on the concentration, you know. So in this face mask, what we did is a very, very tiny amount of this compound, so that they would be non-toxic for humans, but even able to kill microorganisms. You know, and because benzalkonium chloride is also used for colidium, for your eyes for infections, and they have a lot of application. Even when you wash your mouth with these drinks that they have for infections in your mouth, they contain many of them ammonium quaternary and ammonium compounds. So it depends on the concentration, but like any other compound.
So
if it's a high concentration, they can be very toxic, yeah, for sure.
So it is especially important then that no dust from the mask, dust containing the compound, get into our lungs?
Yeah, what we did to study that was to perform this cytotoxicity test, that what you do is to make an extract for 72 hours of the filters, and then you place this extract in contact with human cells and see if it affects the human cells or not. And we did this experiment, and we achieved the right concentration, that it would not affect the very low concentration, that it would not affect the human cells. So we have also always developed a technology with a very, very low amount that was able to kill the microorganisms, the virus or bacteria, but not to be toxic for us.
Yes. Thank
Good.
you very much.
Welcome.
Thank you. Let's go to Albert.
Angel, congratulations for incredible accomplishments. My question is on the standard mask that we've been wearing for the last 2 years for COVID. I recall the photograph you showed us with 3 side-by-side masks. And the one on the left, which you said was the normal one, unprotected, the spacing between the fibers were 50 to 100 micron in your photograph. And the virus is sub-micron. So how could that mask do anything? Does that make sense?
I didn't understand well, sorry. Sorry.
The porosity of the mask has a spacing between the fibers of 50 to 100 micron. And if the COVID virus is 0.1 micron or so, it's going to go straight through. So was wearing these masks really useful?
No, it's because when you have a face mask, you don't have only one filter. You have 5 layers, 5 layers of this filter that you saw in electron microscopy. So they overlap, and the porosity was much less reduced. And also these fabrics, they have electrical charges that they attract the viruses and bacteria. So
So, so the virus independent of the spacing, the virus interacts with the coating, and it may be electrostatic interaction or otherwise, but that interaction effectively corrals the virus so that it does not pass into your lungs. Isn't that correct?
well, some of them pass, but most of them no. You know,
Yeah. Well, of course.
that's why you can get also infected with using a face mask. But sometimes they said that way, because of the amount of viruses that they pass through, it's not enough to make you have the disease. You know.
Yeah. Albert, it's an interesting question by a guy who knows something about microscopy. So go ahead, Albert.
Well, I have a mask here in my hand, and it looks like it's only 2 layers, not 5.
Yeah,
And
that's
sorry? And
no,
is
I
there
know
coating in it?
that's because that protects you less than the N95, that is 5 layers. This is
Right,
a hygienic mask, no? It's called. Or...
No, I understand the N95 is good, but most people are not wearing that. They're wearing this thing that you get free at the hospital.
Yeah.
And that mask is very bad for aerosols, because when you wear that mask, it gets open on the right and on the left, you know. So the aerosols can go through and you can breathe them. So the best mask, I think, is to use an N95, that you get more protection.
No, I understand, but
I
a lot
know
of us,
that
Yeah, like this.
I think
a
it's
lot of us are wearing it.
It sounds like, Albert, it sounds like it's a matter of degree. I mean, some masks are going to be more effective than others, but I'm sure your concern. I understand what you're saying.
Yeah, but that mask is
I promised on how that we would end in an hour and a half, and we're getting dangerously close to that. So I want to go to Steve and to Ron before we end. Steve,
Thank
you're
you.
up next.
Yes, I wanted to ask if it's understood just how cranberries kill viruses. Is the mechanism known?
Yeah, it's because they contain proanthocyanidins. That is a compound that that destroys the envelope of the virus.
What was the name of the compound again?
It is proanthocyanidins. They contain these chemicals that they destroy the envelope of the virus.
Thank you.
Proanthocyanidins, it's called.
Right, Ron, you're going to have the final question for this session this morning. Go ahead.
Thank you. Very, very interesting. Just a couple of quick questions and a comment. Have you examined shelf life issues?
Shelf life, sorry.
How long would
the length? The retention of its capacity to kill viruses and bacteria over time.
Yes, we have studied after storing this face mask to see if the compounds is effective after, and we have demonstrated that even after 6 months, and now we're going into, and also 6 months for sure, that the benzalkonium chloride is very stable, is the best. Cranberry extract is less, it gets less and less effective, because probably because it's natural, or because of but still you can have it for 3 or 4 months stored, you know.
Okay, thank you. Have you any concern that, just like penicillin, if this thing gets widely used, that it will begin to develop its own virus and bacteria resistance. You know, it's the more successful you become, are we exposed to the problem we have with penicillin in you know, becoming self-defeating, if you would.
Well, the bacteria has shown that they also have, they develop also resistance to benzalkonium chloride and also proanthocyanidins, all these compounds. They are able, but using face mask, I don't think is the same way than antibiotics, you know. I no.
Okay, thank you. I just make one last comment about patents. It occurs to me that in your situation, it might be the best for consumers for you to actually get as hard a patent as you can, because then you'll have venture capital interest to invest in it and get it into the marketplace, because it's such a damn good thing to have. As long as the venture capitalists can't see how they get the money back, as noble as it might be, they won't invest.
Yeah.
So sometimes getting a patent provides you a better chance of serving humanity than outside. Yes, Mark.
Interesting point.
Can I just speak to that very quickly too? Because I do have patents.
Go ahead. Yes, sir.
Yeah, it takes three requirements. One, you have to prove your point of conception, which you do with your lab notebooks because they're witnessed. Second, you have to show due diligence, that you just didn't have an idea and write it down, but you actually pursued the idea to make it producible. And the third is most important, you have to maintain confidentiality. Because if you have a public meeting, which this is a public meeting, you have 1 year after that meeting in order to file for a patent, or it goes to public domain. And I really strongly agree with the other folks that you really need to think about at least 1 or 2 patents to fund your research. And I would call Revlon and see whether they might be interested in that lipstick.
I'd also be
If I could
careful
make a
about who
very
you
quick
share.
comment to
Hold on,
Ron's
yeah.
comment. I've
Okay.
been waiting, Ed, so if I can make a very quick comment.
Yeah.
Government, many, many years ago, passed an amendment to the Patent Act, which forbade the patenting of any invention which was made using any government funds. That lasted for a few years, and then studies were made of the effects of that, and they found that inventions supported by government funds very rarely made it into the marketplace. And the reason is, if people couldn't get some exclusivity on their invention, they weren't going to invest in it. Responsive to those studies, the government amended the Patent Act again to remove the requirement and allow people who made inventions with government-supported funds to obtain patents.
And I did just add one quick point. Be careful who you communicate with, because I had a problem in that I shared some of the patentable ideas that I had within a company, and I wound up having to include almost 20 people on the patent because the lawyers said that I had shared that idea with them.
He was
Well,
wrong.
we're gonna close.
Absolutely wrong.
That's
Okay.
what I was forced to do, because I had an
He
email with them on the circulation list.
Let's
That's
it's
what I
like
thought,
about-
but he insisted.
I don't know what time it is in Spain at the moment. It's probably about almost 7. Is it 6 or 7 o'clock in Spain now?
It's fixed.
6. Okay, so I'm gonna give Ron Smith the final word here. Ron, you've heard a lot of conversation, and we know that this is outstanding work. It has great public service. What is your takeaway from all this, Ron?
It's actually the patent discussion, because upon which economics make the difference. If you can't get it to be economically viable, you can't do it.
Yeah.
The only question I would have for everyone around this entire patent situation, and you could do a session on that, Ron, that would be fascinating.
Yeah.
You've got the people who really could add some very interesting perspective to this.
Yeah, I
The
agree.
big question I would have in this is, each person has to determine for themselves when they are inventing how much is enough. And if you can put some constraint on greed to a degree that it makes it more human and humane, I would just want people to think about that a bit in terms of what they're doing and how this works out in the end as far as who gets what.
Gotcha. Angel, independent of the patent question, I just want to tell you that this is a wonderful presentation, a monumental presentation. It really was.
Could I add some?
I know, a loud applause from all of us. What you've done is in the interest of humanity, and you've done it extraordinarily well. So thank you from Winchester, Massachusetts. We're depending on you to do more of this. This is great stuff. Everyone, thank you very much for joining us today. We'll see you again in about 2 weeks.